All right, so in the last video, we concluded with talking about vectors in their component form. And if you'll remember, in component form means a vector is in standard position, where the initial point is at the origin and the terminal point is at the ordered pair v1, v2. So now let's suppose we have a vector, or let's suppose we have some points and we want to standardize a vector and put it in a certain place where it's easier to work with. So what I'm going to do to show you this is I'll start with just the xy plane and then some vector. So this vector here that I'm going to draw, I'm going to label as the initial point P1, which is x1, y1, the terminal point, which is P2, x2, y2. In turn, our vector would be P1, P2 with the correct notation on it. Okay, so let's say we have this vector and we want to put it in standard position. So we want that initial point to be at the origin. So to do this, I'm actually going to go ahead now and put a couple more vectors up here. So I'm going to take a look right here. And since this is the origin, I'm going to call this one OP1 and this one OP2 to keep things kind of neat. Now, this is where you'll have to pay close attention again to that parallelogram law that we talked about when adding vectors. And I would encourage you to go back and look at your notes to make sure everything lines up the way I'm saying it does. If you look carefully at this, what we're going to have is vector OP1 plus P1, P2 vector equals OP2. So, again, pay close attention to how all this works. We're saying that this guy right here plus this guy right here would in fact equal that. And again, I would encourage you to go back and look at your notes and take a look at where the terminal and the initial points all match, and we are in fact correct in moving forward with this. So now, if I'm trying to figure out what P1, P2 is, then I'm just going to subtract the OP1 to the other side. So we would have P1, P2 equals OP2 minus OP1. And then if we go ahead and we write this out using our component form, P1, P2 is going to be x2, y2 minus x1, y1. So remember, for this guy OP2 right here, this would be OP2, and the terminal point would be x2, y2, so therefore the vector in standard position would be x2, y2 using the vector notation. Same conversation with this guy. And now that we know how to subtract P1, P2, this is going to be x2 minus x1, comma, y2 minus y1 vector. And so if we ever have now a vector that's not in standard position, we can simply use this idea right here to replace it or reposition it in its standard position. So let's take a look at an example and I'll show you how this works. So if P1 is going to be 8, negative 3, and P2 is going to be 4, 5, then to find P1, P2 vector in standard position, we're going to take a 4 minus 8 and a 5 minus a minus 3. So all I did there was I subtracted the x coordinates in the correct order, right? The order is going to matter, and then the same thing with the y's. And when we do this, we end up with, of course, negative 4, 8. Now, not a very exciting example to work, but one that's important to take a look at here. If I come over here to my xy plane, and I plot some points, let's say I plot 8, negative 3, so that's going to be over a positive 8, down negative 3, something like that. And then 4, 5, that's going to be over 4, up 5, so maybe something like this. So that's going to be our point 1, this would be our point 2, and so vector P1, P2 would look something like this. Okay? Now, if I look at the vector itself, negative 4, 8, that's going to mean I move from the origin over negative 4 and up 8. So when I do that, over negative 4, up 8, that's going to put me about right here. And as if I connect that and put my arrow on there, well, my picture's not perfect, but you get the basic idea at least. This is more or less me picking up this vector and now moving it over into standard position. Okay, it's still going to have the same length, it's still going to have the same direction. It's just now having that initial point at the origin and the terminal point at the ordered pair, -4, 8. Okay, so now why is it important? Why is it nice to have these vectors in standard position? Well, some pretty nice things can happen that we can do to them when they're in this position. All right, so now that we can put our vectors in standard position, let's talk about how to compute the length of the vector, or the magnitude, sometimes called the norm as well, depending on the text and the context. So to figure this out, I'm going to go ahead and draw the xy plane again. And I'm going to have, very conveniently, my vector v in standard position, which is going to be v1, v2. And then if I want to figure out the length of this, now we can just go back to our basic trig days. And honestly, basic trig, basic algebra as well. And so from here, I know that the distance from there to there would have to be my x-coordinate of the point, v1, v2. So that's going to be a v1. And then we also would know that that's going to be v2. In the rectangular coordinate system, we move over and up. And that's how we get there. Now, we're trying to find the length. The notation for the length of the vector is going to be this guy right here. So double bars on both sides of the vector. The book only uses single bars. Now, I'm personally not a big fan of that, because that also looks like absolute value. And for a student that's just learning vectors for the first time, and we're really going to be working hard on understanding whether or not something's a vector, something's a point, something's a scalar, it's really important to distinguish very clearly what it is you're working with. So I personally will use the double bars on both sides, and I would encourage you to use the same, even though some textbooks, including the one we're currently using, will only use a single bar. There's going to be a really important distinction needed later on between absolute values and then, of course, magnitudes. So just keep that in mind and proceed with caution. So I'm using the double bars to represent the magnitude or the length, and using that Pythagorean theorem, we're going to have v1 squared plus v2 squared. Magnitude or a length is always going to be positive. That's why I'm not including the plus or minus on there. So that's going to be the length of a vector. All right, so now let's talk about unit vectors. Unit vectors are vectors with a magnitude of 1. Magnitude of 1. And so we say to normalize. So to normalize means that we're going to take a vector of any length and we're going to shrink it down to have a length of 1. I'll say u for unit vector is going to be 1 over the magnitude of v multiplied by v. So pay close attention. This is a scalar. This whole thing here is a scalar. 1's a scalar. The magnitude is a scalar. We have a scalar then multiplied into a vector, and our result, of course, would be a vector. Okay, so that's how we normalize. All right, so we'll take a look at an example here. We're going to find a vector that has a length or a magnitude of 2 and points in the opposite direction of our given vector here, v. So anytime where we need a vector to have a certain length, the easiest way to do it is to take that vector, bring it back to a unit vector, bring it back to a vector with magnitude of 1, and then just multiply by whatever length we need it to have. And so I'll start here with v, and I'll create the unit vector with it. So the unit vector here would be 1 over the magnitude of v, which is going to be our -3 squared plus 4 squared, and then multiplied by v itself. So u looks like that's going to be a 1 over 5, since that's going to be a 9 plus 16 would be 25. Square root of 25 is going to be 5. So we have our 1/5 there, and that's going to be multiplied by our -3, 4 vector. So we've got a -3/5 and a 4/5 for our unit vector. Now, before I move on, I do want to take just kind of a sidebar here for a second and convince you that what we've done has changed our length. We just saw the magnitude of this thing is 5 right here. Magnitude of it is 5. And now what we've done, we should have created a magnitude of 1 right here. So let's find the magnitude of our unit vector here to make sure we did this correctly. So that's going to be a square root of negative 3/5 squared plus 4/5 squared. And that's going to be the 9 over 25 plus 16 over 25, which is going to be a 25 over 25, which is, of course, 1. So we've done our job. All right, and so if anything, that's going to convince you that this normalization process is legit. All right, so back to our original problem. We've got a vector now of length 1. We want it to have length 2. So what I'm going to do is multiply this thing by 2. And in doing so, now I'm going to have a negative 6/5 and an 8/5. Now, that takes care of the fact that our vector now has length 2, but we also want it to point in the opposite direction. So to account for that, all I'm going to need to do now is put a negative out in front. That's going to change the direction. And so in doing this, this is going to give us for our final answer a positive 6/5 and a negative 8/5. So that is, in fact, a vector with length 2 points in the opposite direction of the original. All right, so now we're going to discuss standard unit vectors. In R2, you'll have 2 of them. In R3, you'll have 3 of them. So for the sake of including everything, I'll just go to R3 right away. So in R3, you're going to have a standard unit vector. So a standard unit vector means it's going to be in standard position. It's going to have a length of 1, and the I vector is going to be the 1, 0, 0 vector. Okay, so length 1, and it's going to be essentially along the x-axis. The one along the y-axis right here is going to be the j vector, and that's going to be 0, 1, 0. And then the final one that's along the z-axis right here, this is going to be vector k, which would be 0, 0, 1. So I, j, and k would be the standard unit vectors in R3. If you're in R2, your I would be 1, 0, your j would be 0, 1, and you would not have a k. So these would be the standard vectors, unit vectors in R2. Okay, so one of the things that we're going to be able to walk away with now from this conversation is the fact that every vector can be expressed as a linear combination of standard unit vectors. And so if we take a vector, let's say we take vector v equaling v1, v2, v3. If I expand this out, this could be the same thing as v1 times 1, 0, 0 plus v2 times 0, 1, 0 plus v3 0, 0, 1. Now, if you're not seeing that or you don't believe that, you can always check it and try. If I distribute my v1 in there, that's going to give me my v1 and zeros. If I distribute my v2 here, I'll have zeros on either side, and then the v3. Then when I add it all up, it does in fact come back to this. So I would highly encourage you to try that if this is not making sense to you. Now, this 1, 0, 0, that's vector I. The 0, 1, 0 is vector j, and the 0, 0, 1 is vector k. So we've expressed now our original vector as a linear combination. This is a linear combination of addition and multiplication of standard unit vectors. And so the reason why this is so important is it's also another notation for vectors. You'll see this used a lot, but you'll also see this used a lot as well. For example, if let's say vector A was going to be 2i minus 3j plus 7k, this is the same thing as vector 2, negative 3, 7. Some textbooks prefer one over the other. Many times I don't care, but you will see it quite a bit both different ways, and it's important to understand that they are the same thing. This is just a linear combination of standard unit vectors. Okay, so the last thing that I want to mention in this section are the properties of vectors. And I don't really, let me see if I can move this. There we go. All right, so properties of vectors. I'm not going to write these out. These are in your textbook, and most of them are very intuitive. Page 708. So take a look at the properties of vectors on page 708. The one thing that I do really want to point out is that this guy is the zero vector. So it'll be bold, of course, in your text, but that's going to be the vector 0, 0, 0, whereas this would just be the scalar 0. So the notation is incredibly important, distinguishing between scalars and vectors. Pay close attention to that as you read, pay close attention to that as you do your work, as you write, to make sure you are in fact saying what you need to say in terms of scalar versus vector.